Hello everyone, welcome to the course on architectural design of ICs. So, we are seeing various actually this clock divider circuit. So, we have already seen the architecture for clock divider where the division, that means the division factor is in the power of 2, and if it is not in the power of 2, then also with the 50% duty cycle, that also we have seen, that means the division by 3, division by 5. Okay. So, that we have already seen. Then we will see some other actually clock divider circuit which will be done using the hardware, and whenever we are seeing, at the time we have also seen that at the very last, to make the 50% duty cycle, we have to put some extra OR gate to maintain. Otherwise, if we do not use that particular logic, the generated this waveform, that will not be of 50% duty cycle. So, to make it 50% duty cycle, we have to use this extra logic circuitry to maintain the 50% duty cycle, though it should be divided by 3 or divided by 5. Now, today we will see then again another example, which is divide by 6 counter. So, in divide by 6 counter, actually we need 3 different flip flops which will count, and here I need one this Johnson counter, 3-bit Johnson counter. So, something like this. So, in Johnson counter, if you are having, so at that time, that means this, if you design one this 3-bit Johnson counter, that will be act as perfectly 6 divided by 6 clock divider circuit. Okay. Now, actually if we divide by 7 counter, so divide by 7 counter, it requires one mod 7 counter, and it has 8 possible states, which by which it needs only that means the 7th state is basically useful. Okay. So, for this particular actually divide by 7. So, divide by 6 means only you need 3-bit Johnson counter. 3-bit Johnson counter will give you the divide by 6 counter or divide by 6 clock divider circuit with 50% duty cycles. You do not need the additional hardware, or that means you do not need to design one mod 6 counter and then other logic, you do not have to do. Using one 3-bit Johnson counter, you can that means make the circuit of divide by 6. So, to make this divide by 7 counter, where this 7 particular state will be used, and here you see you notice that this for 0 0 0, the output of the third flip flop is high for 3 clock cycles and low for 3 clock cycles. Pass this output to one more flip flops which will work negatives of the clock, then make ORing of these two output. Indicates what? Actually, this is the logic for this mod, that means this mod 7 counter, and then again just like this, the corresponding outputs from this QB, they are basically connected with the Y to make 50% duty cycle. So, here you see that QA is this one. So, this is this QA, the corresponding logic for, that means the waveform for this QA is this. Then we need what? We need this QD is nothing but this QB. So, QB, and then again we will get something like this. If we just add these two, then we will get the corresponding Y output, which is nothing but division by 7 factor. Okay. So, now here you see how you can measure that. Okay, 1, 2, 3, 4, 5, 6, 7. So, up to 7 clock pulse, now your output is basically extended with the cycle of 50%, and everywhere, every of this particular whether you are designing this divide by 7 or divide by 5 or divide by 3, any of this circuit, here you consider that the final flip flop, they are of negative edge triggered. If all these flip flops are positive edge triggered, this is of negative edge triggered, and as this is of negative edge triggered, because of that we are basically getting this divide by 7, divide by 5, divide by 3, something like that. Otherwise, we could not have get this divide by 7, and that is why you see in this that means in this waveform, it is at the corresponding negative edge, up to this negative edge it is getting this, that means it is extended. So, this q a and q d, if you see that this q d, it is getting the output because this particular flip flop is negative edge triggered. So, that is why whenever it that means finds this negative edge, then only it changes its value. Okay. So, here also by that, by using this negative edge triggered and then using this extra OR gates, we can make this happen, that okay, we can make this divide by 7 with 50% duty cycle. Okay. So, then again another example, that I need one counter which will be divide the clock by 9. Okay. So, at that 9 we will be having total 16 possible state, among them only the 9 state will be used. Okay. So, here you can actually observe that the third flip flop output value is low for 5 clock cycles and high for 4 clock cycles. The output is required divide by 9 clock signals, but not 50% duty cycle. So, to make this 50% duty cycle, pass this output to one more flip flop triggered with negative clock edge, and then make ORing to these two signals to 50%, make it 50% duty cycle. Okay. So, that is why how many to make this divide by 9, how many flip flops I require? 5, 4 for this and one extra to make that output of 50% duty cycle. So, if you see that 4 of this divide by 9 logic, okay, and then the corresponding output is now OR with this q b, which is coming over here, and then if you just OR, you will get the corresponding output sequence something like this. So, that means here the q b is this one, q b you will get this one, then depending on that what will be the q e, sorry, this d e or this q e will be depending on the corresponding that negative edge triggered values. So, in negative edge it is find that okay 1, so it will be extended up to this, then again it is just extended. So, here you will get that 1, 2, 3, 4, 5, 6, 7, 8, 9. So, up to 9 this particular q b plus q e is extended. So, now if I ask you to design one divide by 10 counter. So, divide by 10 counter you require again the Johnson counter with the terminal count of this 9 and only of 4 bit Johnson counter with the terminal count of 9. So, whenever it will find that okay, it is counting from 0 to 9, after that again it will come down to 0. So, which will make you the divide by 10 counter. So, now again divide by 11 counter if you want to make, then you again you have to consider something like this. So, there will be 16 possible state, but among them only 11 state will be used. So, based on that you find out this particular logic to make that mod 11 counter, and then you put this extra logic to make that means 50% duty cycle. So, this output at this output, this logic you can put to make 50% duty cycle. So, then this is actually by this way you can design or you can that means develop any clock division circuit or the multiplier circuit also we have already seen. Now, we will see another that means different example is that this is one of the techniques which we apply whenever we use actually, or this is the tips or this is the tricks what we use if we find some problems whenever we declared the corresponding functions. Declare the corresponding function means we suppose this one is the code for one particular logic. Okay. So, what is this code says that if one this is the function state, the logic says that when wait is activated, the signal wait is activated, then if critical is another signal, then target will be goes to, that means the source 1 will be goes to the target. Otherwise, if the that means the net critical is not active, so at that time source 2 will be assigned to the target. So, this will happen, this logic will happen when the state is wait state. When that is in the active state, so at that time the critical, if the critical is another actually signals, when the corresponding signal critical is 1, then target will be source 1, otherwise this target will be from source 3. Okay. So, now depending on this, actually what I need is that, so the state and I need the signals which is this critical. Okay. So, when this wait state, if the critical signal is 1, then it will select the source 1. If it is 0, so that means if the critical signal is not active, so at that time it will select this source 2 which will go to the target. But when this active state, then again in active state this will be in active state, this will be source 1 and source 3 and this will be the critical, right. Now, as we can see that from both of these particular things, both of these, that means I need two of these, one for active state, another for wait state, where this source 1 is fixed, is common to each of these state, and only the other terminal which is the source 2, that means the here for this wait state, that is different for active state which is this source 3. So, to make this particular logic, okay, to make this particular logic in use, that means in a single code. So, how we can modify is that if critical is 1, then all the time for all the with irrespective of the wait state or active state, whenever this critical signal is active, the target basically is assigned to source 1, and if the critical net or the critical signal is not active, at that time that in wait state the target will be in source 2, in active state the target will be come down to source 3. So, what we can do? We can have only one multiplexers where this critical is the select line and the source 1 is both common for wait state and the this active state. So, the state will be the other select, it goes to the other select line in, that means other input, where when this critical net is 0. So, at that time it will select depending on the state whether that is wait or active, it will select the source 2 or source 3 to the circuit. So, this is one of the example, that means if we that means this is the initial description of the code, and based on that we can make the corresponding circuit. But if we modify the same code in the other way, at that time, that whenever this critical is, this indicates what? We have to wait to check which state it is, but here we do not have to check. When the net signal is that critical is active, immediately the target will be assigned to source 1, where in this particular case we have to check the whether the critical is 1 or 0 depending on the state. First we have to check the state, which state it is, whether that is in active state or whether that is in wait state. Then we have to calculate, we have to that means check whether that critical net is active or the critical net is not active. If it is active, then select source 1, if it is not active, then select source 2. In wait state, if in active state, if this critical is 1, then source 1 or else source 3. But here in this case we do not have to consider the state for the critical condition. Whenever the critical condition is on, so automatically the target will be assigned as the value of source 1. And when the critical is not active, then only I will check whether that state is 0 or whether that means the state is active or whether the state is wait. So, depending on that, then I will assign the target value. That means, at that time I do not need immediate action. So, that is why here actually this tricks is known as this late arriving signals prioritization. Okay. So, the priority is being given to the corresponding this particular critical net, irrespective of the what state it is, as this the corresponding logic demands the, that means the critical, the priority instruction to the critical net. Okay. So, this whenever we will design the circuit, so at that time this small modification will make your design so much efficient. Okay. Then another example we will see this late arrival signals. So, late arrival signal means, suppose one logic is this, that begin if A late plus B greater than equals to max, then out equals to C, else out equals to D. So, A late means this is the signals which is coming from another logic and it is coming very lately to this particular port. So, according to the logic, what we have to do? A plus B we have to check, that is whether that is greater than equals to max, then the output of that will decide that okay, we have to select C line or D line to the output. So, then what will happen? What is the problem in this particular circuit is that, as already this A late signal is coming late. Okay. Let us say this A late signal is coming late by 10 nanosecond. Okay. So, then again if this particular block is having 5 nanoseconds of delay and this block is having 3 nanoseconds of delay and this multiplexer again is having 1 nanoseconds of delay. So, then total after 10 plus 5 15 plus 3 18 plus 1. So, total 19 nanoseconds I will get the output at this particular out. So, irrespective of doing that, what I can make is that I will just change this logic to B minus max greater than equals to A late, then out equals to C, else out equals to D. That means, keeping the logic same, I have just, that means shift this max to this, A late to this particular side. So, then what is happening? Initially we have to calculate this B minus max and then we have to calculate with this ALH signals whether that is greater than equals to, and depending on that this will generate the corresponding signals which will decide that the output will go to C or D. Among these C and D, what value will go to out. So, in this particular case what we have considered, so this signal is coming let us say 10 nanosecond. So, this is having 5 nanosecond, this is of 3 nanosecond, this is taking 1. So, total is 10 plus 5 plus 3 plus 1. So, total 19 nanoseconds it requires to complete the full operation. Why? Because unless and until this particular signal is arrived, I cannot start seeds operation. So, once this operation is not yet complete, I cannot start this operation. Once this particular operation is not yet complete, I cannot start this operation. So, that is why the total summation of the all these paths delay information will be the maximum computation time for this particular circuit. Whereas, by making these small changes in the logic, now what if I say that okay, the adder and the subtractor will be having the same delay, let us say this is of 5 nanosecond, and now this is coming at 10 nanosecond, this is of 3 nanosecond, this is of 1. So, now whenever this 5 is already coming, 10 is also parallel which is coming from other signals. So, at that time the max of these two paths will be considered. Here what is happening? 10 plus 5, but here among of this 10 and 5 which one is the maximum one? So, 10. So, it will consider 10 is the maximum delay for computing these two particular path, plus then again to that means complete this task I need 3 plus 1 means total of 40 nanosecond in this particular case. So, that means the logic remains same. In this case I need 19 nanoseconds to complete the full task, but in this case I need only 14 nanoseconds to complete the full task. Okay. As because I made this corresponding modification to make this to, that means while this particular signal is not coming, by that time I am completing the corresponding task over here. I am not waiting for the signal which I am waiting here in this particular example. Okay. So, this is one of another actually tricks which we use in case of optimizing or to improve the performance of our circuit. Okay. So, it is not that only these are the, that means tips and tricks which are there. So, it depends upon you while you are designing. So, at that time how, that means depending on this whether you have to do the priority selections, or if one signal is already coming late. So, you have to do some kind of this modification. So, everything depends upon you how you, that means how you can tackle the problem to get one circuit or to design one circuit which will be much more that means the performance of the circuit will be much more on the enhanced side. Okay. So, this is that means this is some of the that means tips and tricks which what we have already which we use in case of digital circuit design or digital integrated circuit design. Okay. So, it is not that this is enough. So, there are so many. If you need more information, then please let me know through discussion forum. I will provide you more information, or I will provide you the documents where you can find more on this. And people are basically doing research every day to improve the performance day by day on this while they are doing this hardware design of digital integrated circuits. So, with that, thank you for today. Again we will see, and that means some other topic on this architectural design of IC.